everyone. My name is Harnit Saini. Today the topic of our discussion is paging and segmentation. Now, first of all, we should know what is paging. Logical address space of a process can be non-contiguous. Process is allocated physical memory when the latter is available. Divide the physical memory into fixed sized blocks called frames, and size is power of 2 between 512 bytes to 8192 bytes. Divide the logical memory into blocks of the same size called pages. Keep the track of the all free frames. To run a program of size n pages, need to find n free frames and load the program. Now set up the page table to translate a logical to physical address and internal fragmentation. These are the things which are related to paging. Now, what is the concept of paging? There is one physical memory, right? It is divided into fixed size blocks, and that blocks are called frames, right? Now, we have one logical memory, right? It is also divided into fixed size blocks, and that are called pages, right? These pages are mapped to some function, and they are some function is calculated, and they are mapped to the frames in the particular physical memory, right? So how it is done? Let's explain. Now how the address translation scheme is done. Now there is a page number P used as an index into the page table, which contains the base address of each page in the physical memory and the page offset combined with the base address to define the physical memory address that is sent to the memory unit, right? Now the page number, the logical address is divided into two parts, right? First is P, means page number, and second one is D, that is the offset. Page number means out of so many pages, which page is selected, right? Like this is 0 page, 1 page, 2, 3 page. We have selected, suppose, page number 1, right? Like we are searching in the book, right? We have to go to page number 1. D means on this page number 1, at which place you have to go. Means page 1, paragraph 2. Paragraph 2 is the offset and page 1 is the page number, right? This way we will understand now. Now see here, there is a CPU, right? CPU will generate one logical address, which is divided into two parts, P and D, right? P is the page number and D is the offset. Now we will maintain a page table. On this side, we will write all the page numbers, and this side we will write all the frame numbers. Which page is in which frame, right? One index table type thing is there, right? Then from here we will go to the particular page. We will suppose that one page is searched, right? We will go where the page number 1 is written. Suppose it is written here, right? We will pick the F from here, right? Means the frame number from here, that I got F, right? I got F from here, and I know the page size is equal to frame size, right? Then that means the offset is same in both the cases, right? I will take P, from P I have mapped F. F I got, I will combine this with D and I will get the physical address, and here I will get the frame number, and in that particular frame at which place I have to go, I will calculate it from D, right? Now let's take one question. Consider a logical address space of 8 pages. Now suppose there is a logical memory, it has 8 pages, 0, 1, 2, 3, 4, 5, 6 and 7, right? These are the 8 pages, and of 1024 words each. means the size of each page is this much, means the page size, right? Mapped onto physical memory which have 32 frames. Now this is the physical memory which is larger than the logical. This is the logical memory, this is the physical memory, right? It have 8 pages, right? And it have 32 frames. This is the question, right? Now, they are asking how many bits are there in the logical address. Now, for this, we have to generate one address, that is P and D, right? This is the page number now. This is the page number. Their page number can be told by how many pages you have. This will depend on number of pages. Number of pages. Number of pages are 8. 8. So this can be written as 2 raised to power 3. Right? So 3 bits we will require for page number. Right? And now comes the offset. Offset means the position in that particular page. Right? And that will come from page size. Page size is 1024. That means 2 raised to power 10. That means for this we will require 10 bits. For this 3 bits. So total in logical address we will require 13 bits. Right? Now we will go for physical address. Physical address we have 32 frames. Right? In 32 frames means 2 raised to power. Now frame number and D. This is the physical address. Right? This will come from frame numbers. These are frame numbers. 32 means 2 raised to power 5, right? And D is same in both the cases. So 10 bits here for D, so 10 bits here for D, right? And for F we require 5 bits, right? Total 15 bits for physical address. Now see how it is being mapped. See, in the logical memory we have 4 pages, P0, P1, P2 and P3, right? These page numbers will be written on the side of the page table, 0, 1, 2, 3, and these are the F. 0th page is on the first frame, right? First page is on the 4th frame. Second page is on the 3rd page. Third page is on the 7th frame, right? This way the mapping is done. Now, how these pages are created or page table is created. Now we can see before allocation, these are the pages which are available. We have what frames we are having free. We have 13, we have 14, we have 15, we have 18, we have 20, right? This is 13, 14, 15, 18 and 20, right? We will keep all these free frame list here. Now we know that we have 1, 2, 3, 4, 5 frames free, so we can map 5 pages in that, right? So for a new process we will bring and we will divide it into number pages. Suppose it is divided into 4 pages now, right? 4 pages and some new processes there. Now we will write how these pages will be used for by this new process, and that pages will be mapped to the memory. Now see here, pages 0, 1, 2, 3, 0, 1, 2, 3, and wherever these frames are kept. Now we have first page 0, 14th, this one, so this will be mapped here. This was one of the free frames there, right? Then page 1 is kept on 13th here. This is also one of the free frames. Page 2 is kept on 18th. This is from free. And page 3 is kept on 20. This is also one of the free pages, right? Now, the associative memory means we can say the memory like translation looks like buffer memory is also there, where we can, for the quick access, we can keep that page number and frame number in that. Those pages which are frequently used again and again and again. So first we have to search the page table, then we have to search the memory. So it will take a time. So what we do is we bring a intermediate memory in that is associative memory. We will keep those pages which are frequently used in that particular, so that they can be quickly accessed, right? In that memory, there is a page number, there is a frame number. So, okay. Address translation is A to A dash dash. A dash is the associative register or get the frame out. Otherwise, get the frame dash from the page table in the memory, right? Now, this is the register here. And if the page is when the page is required, it will be searched in the associative memory. And if the page is not there, then it will search into the page table. Okay, this way we can reduce the time of the searching a page which are frequently used. Now see the diagrammatic view, what is happening here. CPU is giving one logical address, right? Suppose we got some page number here. We will first search in TLB, right? If we get a TLB, we get that page in the TLB, then it is a TLB hit, right? And we will suppose we are searching for this particular page. We got the frame number here. We will combine that frame number with the offset and we will get the physical address. This was the case in case of TLB hit, means we got the that particular page in the associative memory. Now TLB miss. When we doesn't got the page in the TLB, then what to do? Then again we will do the same thing which we were doing earlier. We will search in the page table, pick out the frame number, we will combine with D, and then we will get the physical address. Right? Memory protection. Memory protection implemented by associating protection bit by each frame. How can we do this? Valid or invalid bit attached to each entry in the page table. Valid indicates that the associated page is in the process logical address space and is thus a legal page. Invalid bit indicates the page is not in the process logical address space. Right? This, from that particular bit, we will come to know that particular page we will find in the page table or not. Right? We will find it in the logical memory or not. Now see here, page 0, 1, 2, 3, 4, 5, right? Now the page table will have two entries, one for the frame number and other for the valid, invalid bit. Now this particular page, page 0, right? Now we have pages till 5, 0 to 5 only. 0 to 5 will all have valid bits because this is in the page table, it means they are present in the logical memory. 6 and 7 are not there in the logical memory, so their bit is set as invalid, which says that it is not there in the logical memory. Right? Now there is a different types of paging. First is two-level paging. A logical address space, if increases from 32 bit, right, with 4K page size, then it can be divided into page number consisting of 20 bits and page offset consisting of 12 bits. With the earlier procedure, what we will do. Since the page table is page, the page number is further divided into a 10-bit page number and 10-bit page offset. Now we can divide the page table into two parts now, right? Now the page number will give two things. First page number will give the page number in the first page table. This will give the page number in the second page table. This is P2, this is P1. And finally, we will get a frame number which is added with that offset and we will get the physical address. Right? Where Pi is an index into the outer page table and P2 is the displacement or offset within the page of the outer page table. Now you see what is actually happening. See, we are in the logical address, we are having P1, P2 and D. For this outer page table, we will see only this part of the address, right? We will not see this. Now, P2 is the offset for P1, right? For this particular address, P1 is the page number and P2 is the offset for that particular address. Means we will search P1 here and we will take the offset from here. Means we will find out where is P2. Then from here, whatever value is there, we will search it there, right? And whatever frame we get here, we will combine it with D and we'll go for physical address, right? Hashed page table, the other type of page table, a common approach for handling address spaces larger than 32, right? 32 bits is to use a hash page table with the hash value being virtual page number. Now there is another method when the number of pages are large enough, means we are having in 32 bits long logical addresses, more than 32 bits, then it is the best option to use hashed page table. In that, what we have to do, each entry in the hash table contains a linked list of elements that hash to the same location, right? Each element consists of 3 fields: virtual page number, virtually mapped page number, and pointer to the next linked list. Right? Here we have to use linked list because more than one page can be hashed to the same location. So here we have to maintain that which record in that particular location has to be accessed. So that is done with the linked list. So with this diagram I will show. Now there is a physical address, right? Physical address will give you the page number and D. Suppose your hash function is some x modulo 11 or 4. Okay, you take it 4, right? Now this page number will be divided by 4 and whatever is the remainder, that is the position in the hash table. I'm taking an example for this, right? What type of remainders you can have in case of modulo 4? You can have 0, 1, 2, 3, right? These can be the remainder in case of modulo 4. Now, many of the pages will give the modulo answer 0. All those particular pages will be lined up in the same location, right? And there will be a pointer which will tell that what is the next data. Suppose we are searching R, we will hash that location first. We have found that this particular location is there where R is stored. Now we will see where R is. We will keep on moving until we get R, right? And we will go to one record to other record with the linked list value, with the pointer value which tells us where is the next record. And finally we will get that R and we will combine with D and get the physical address. Inverted page table, one entry for real page of the memory. Entry consists of virtual address of the page stored in that real memory location with information about the process that owns that page. Decreases memory needed to store each page table, but increases the time needed to search the table when a page reference occurs. Use hash table to limit the search to one or at most a few page table entries. Now see what is actually done in inverted page table. See, we are having the process ID also, right? Process ID and that particular page number is the one entry now, right? Earlier what we were doing, we were writing page numbers here and F here. But now we will write I here, means the physical memory number, frame number, plus the PID and P combination will be written inside the table. Now we have to search this combination in the page table. Wherever we get this combination, we will pick that number and we will combine it with D and we will get the physical address. This is called inverted page number, right? Now there is a concept of shared pages. 2 or more processes can share the pages kept in the memory. So no need to store it again and again and bring that pages again and again to the memory. So what can be done? One copy of read-only code shared among the process, text editors, compilers, Windows systems, etc. Shared code must appear in the same location in the logical address of all the processes. What we'll do, we will keep that location, which are shareable location, in the logical memory of all the processes. And the private code and data, each process keeps a separate copy of the code and data. The pages for the private code data can appear anywhere in the logical address space. Like you see here, this ED1, ED2, ED3. This is the shareable data which all the process 1, process 2 and process 3 is required. So these ED1, 2, 3 are kept in 3, 4, 6, right? So this means these addresses are included in the page table of all the processes. And the other one where the non-shareable data is there, you can give the different addresses there, right? Now what is segmentation? Earlier in paging scheme, we were dividing the blocks into blocks of same size. But there can be a loss of code, or we require contiguous blocks so that the whole code can be kept at one place. But here we are solving the problem in segmentation, where we can logically divide the process into different blocks, right? Memory management scheme, let's suppose user's view of memory. A program is a collection of segments. A segment is a logical unit, such as, like in one program, we can keep main program in one block, procedure in one block, function in other, method, object, variables, common block, stack, symbol, table, arrays, etc. These can be kept separately in different blocks, right? Now see here, user's view. Here there is a logical address space. Now that program is divided into different modules, you can say, and all are of different sizes, right? See here, these are the different sizes of segment, and they are kept in the memory in this way. Sizes are also different here. Here we are not saying that the page size, we will not say page now, we will say segment. Segment size and frame size are to be same now, right? Now what? Segmentation architecture, logical address will consist of two parts, segment number and offset. Like in physical logical address, in paging, what was there? P and D, here S and D, segment number and D. Segment table maps to two-dimensional physical addresses. Each table has an entry. For page table, we were having only one entry which was telling the frame number. Now it will have two entries. It will tell the base, means from the starting address where that particular segment is starting, and it will tell us the limit, means the length of that particular segment. So we will add that limit and calculate the ending address. Segment table base register points to the segment table's location in the memory. Segment table length register indicates the number of segments used by the program. So segment number S is legal if S means the size of S is less than the limit. Now let's take an example. On a system using simple segmentation, compute the physical address for each of the logical addresses given the following segment table. If the address generates a segment fault, indicates so. Now we have four segments, 0, 1, 2, 3, right? Now their base addresses are 1100, 2500, 200 and 4000. This is the length, means the segment that is starting from 1100 has length 500. So the program that can fit from 1100 and the size of 500 only can be fitted at the starting address 1100, and the segment of 1000 can be fitted on 2500. Similarly, 600 can be fitted on the address 200. Size 1200 can be fitted on address 4000. Now we have the first one, right? First one is the segment number and second is the limit, right? This is the segment number and this is the limit. Now we will map this. A is the 0th segment and 300 is the limit till which this segment has to be stored. But we have the limit 500, so 300 can fit in 500, right? So this is okay. So what will be the address now? 1100 is the starting address and 300 is added to it and we get 1400, right? Now the second segment, this one. 800 is the limit of the process that has to be fitted in that. That has to be routine which module that has to be fitted in that. But the size is only 600 here. But the limit is 800. The size is 800 and limit is 600. So it is larger. This size of the program is larger. So this cannot fit here. So it is a fault. Means it will generate an error. Now 1 and 600. 1 and 600 is the size of the segment, and here the size of 1000 can be fitted. So 600 can fit in 1000, so it is okay. So starting from 2500 we have to add 600, right? The ending address will be 3100, right? Thank you very much.